Yeah. Hello all. In my last class, I discussed IV relationship in a PN junction, right? That is our diode current equation. That is I equal to I naught into e power V by Vt minus 1. And also we derived voltage across the diode, right? Yeah. In this lecture, I will start with temperature effect on diode current. What is the next topic? Temperature effect on diode current. Yeah. Put the heading. Temperature effect on diode current. Right. You know, the diode current is affected due to temperature in two ways. The diode current is affected due to temperature in two ways. One is reverse saturation current, another one is cutting voltage. One is reverse saturation current, another one is cutting voltage. So first, I will start with temperature effect on I naught, right? See here, temperature effect on I naught actually. See, as temperature is increased, what about the intrinsic concentration? Increases. If intrinsic concentration increases means what about the reverse saturation current also? Increase. Because we know I naught equal to E into A into Ni square, right? If Ni increases means what about I naught? I naught also increases. If I naught increases means what about I also? Increases, right? In this way, the diode current is affected due to temperature because of reverse saturation current, right? See how it is affected actually. See, when the temperature is rises, reverse saturation current rises, right? Yeah, how it is affected. So first we will discuss about theoretically actually. Theoretically, right? For silicon, per 1 degree rise of temperature, per 1 degree rise of temperature, how much of reverse saturation current increases? 7% of reverse saturation current is increased, right? Similarly for germanium. For germanium, per 1 degree rise of temperature, how much of reverse saturation current increases? 11% of reverse saturation current is increased. This is theoretically, right? Coming to practically, coming to practically, per 1 degree rise of temperature, per 1 degree rise of temperature, how much of reverse saturation current increases? 8% of reverse saturation current is increased. Okay. Similarly, I will also define per 10 degree rise of temperature. See, in case of PN junction, per 10 degrees of temperature, how much of reverse saturation current increases? You know, reverse saturation current become doubles. Reverse saturation current become doubles. Okay. Next, I will also define reverse saturation current at any temperature. Reverse saturation current at any temperature is nothing but I naught of Tn is equal to I naught of T naught into 2 power Tn minus T naught by 10. This equation gives reverse saturation current at new temperature. See here, per 10 degrees of temperature, reverse saturation current becomes what? Doubles, right? See, if you substitute Tn is 10, then you will get 2 times of I naught of T naught, right? That means the reverse saturation current will become doubles, right? Yeah, write down this. Diode current is diode current is affected due to temperature, affected due to temperature in two ways. In two ways. The first one, write down temperature effect on I naught. Temperature effect on I naught. Yeah. Copy this flow graph. Also copy this. After flow graph, copy the theoretical and practical values. Yeah, right on. Reverse saturation current at any temperature is given by reverse saturation current at any temperature is given by right on, I naught of Tn equal to I naught of T naught into 2 power Tn minus T naught by 10. 2 power Tn minus T naught by 10. Right. This is one case. And the second case is temperature effect on V gamma. Temperature effect on V gamma. Yeah, this is case 2. See all of you. See, as temperature increases, what happened? Intrinsic concentration here. Intrinsic concentration is increased, right? If intrinsic concentration is increases, then what about the built-in potential? Decreased, right? We know the built-in potential equation, that is V naught equal to Vt into ln of Na into Nd by Ni square. Already we derived this expression in our previous lectures, right? Okay. See here, if Ni is increased means what about the V naught? Decreases. If V naught is decreases means what about the cut-in voltage here? Decreases, right? So in this way, the cut-in voltage is affected in temperature. Because of this cut-in voltage, actually the diode current also affected, right? Here theoretically, how it is affected actually, right? See, for silicon, per 1 degree rise of temperature, how much of cut-in voltage is decreases? 2.1 millivolts. See, this minus indicates decreasing, right? Similarly, for germanium, per 1 degree rise of temperature, this is simply 2.3 millivolts. Okay, and practically for both silicon as well as germanium, per 1 degree rise of temperature, how much of cut-in voltage is decreases here? 2.5 millivolts cut-in voltage is decreased. Similarly, per 10 degree rise of temperature, see, per 1 degree 2.5 millivolts, and for 10 degree how much? Just simply it is 25 millivolts. Cut-in voltage is decreased. Okay. I will also define cut-in voltage at any temperature. What is cut-in voltage at any temperature? That is V gamma of Tn is equal to V gamma of T naught minus delta T into 2.5 millivolts. This equation gives cut-in voltage at any temperature. Yeah, write down please. Case 2. Copy this flow graph. Copy these theoretical and practical values. Yeah, write down. Cut-in voltage at any temperature is given by V gamma of Tn is equal to V gamma of T naught minus delta T into 2.5 millivolts. Delta T into 2.5 millivolts. Yeah. So in this way, the diode current is affected due to temperature, right? Yeah. Right? Any problem here? Right? Any question? Right on. A diode has reverse saturation current. A diode has a reverse saturation current of 10 microampere, 10 microampere, sorry, reverse saturation current of 10 microampere, and cut-in voltage of 0.7 volts. Cut-in voltage of 0.7 volts at room temperature. At room temperature. Find reverse saturation current. Find reverse saturation current and cut-in voltage at 52 degree centigrade. At 52 degree centigrade. Yeah. See, once again, I am repeating the problem. See, a diode has a reverse saturation current of 10 microampere and cut-in voltage of 0.7 at room temperature. Find reverse saturation current and cut-in voltage at 52 degree centigrade. This is our question, right? Yeah. See, what is our given data actually? The given reverse saturation current. How much? 10 microampere. Also, the given a cut-in voltage. How much? 0.7. 0.7. At what temperature? 27 degree centigrade. That is room temperature, right? See, if this temperature is increases to how much? 52 degree centigrade. 52 degree centigrade. What is the reverse saturation current and what is the cut-in voltage? Right? Yeah, that is the question. Yeah, how to calculate reverse saturation current at any temperature? What is the formula? Reverse saturation current at any temperature is nothing but I T naught of Tn. I naught of Tn is equal to I naught of T naught into 2 power Tn minus T naught by 10. Okay. Here we want to calculate reverse saturation current at 52 degree centigrade. Right. See here. What is I naught at 27? I T naught is nothing but 27. This is 2 power 52 minus 27 by 10. Right. I think what is this value actually? Reverse saturation current at 27. How much? This is 10 microampere. This is 2 power 2.5. So how much it is? This is simply 56.56 microampere. This is the first bit, right? Next, similarly, cut-in voltage. What is the equation for cut-in voltage at any temperature? That is V gamma of Tn equal to V gamma of T naught minus 2.5 millivolts into delta T. What it is actually? V gamma of T naught means cutting voltage at room temperature. How much it is? 0.7 minus 2.5 millivolts into delta of T. How much? 52 minus 27. This is simply 0.637 volts approximately. Right? Copy. Next topic, diode resistance. Next topic, diode resistance. Right. Yeah. See, diode exhibit resistance. See, any material exhibit some resistance. I think you know resistance is nothing but oppose the flow of current or oppose the flow of charge, right? Here my diode exhibit two types of resistance actually. One is static resistance. Another one is dynamic resistance. Is dynamic resistance also called as small signal resistance? Okay. Here, diode exhibit two types of resistance. One is static resistance, another one is dynamic resistance. First, what is static resistance? We will talk about static resistance. See, static resistance is nothing but it is the ratio of voltage across the diode to the current through the diode. What is voltage across the diode? V. And what is current through the diode actually? I. This is called as what? Static resistance. The static resistance is denoted with capital RDC. Okay. You know, this static resistance is calculated under presence of DC source. Right? Yeah. Write down this. Write down. Diode exhibit two types of resistance. Two types of resistance. Diode exhibit two types of resistance. The first one, static resistance. The first one, static resistance. Second one, dynamic resistance. Second one, dynamic resistance. Yeah. Next heading, static resistance. Next heading, static resistance. Right on. It is the ratio of voltage across the diode to the current through the diode. Current through the diode. That is capital RDC is equal to V by I. Capital RDC is equal to V by I. It is calculated under presence of DC source. Under presence of DC source. Right? Yeah. And next heading, dynamic resistance. Dynamic resistance. That is denoted with small RAC. Denoted with small RAC. Right. Yeah. So now, here first of all, what is dynamic resistance? Dynamic resistance is nothing but it is the ratio of change in voltage across the diode to the change in current through the diode. Change in voltage across the diode to the change in current through the diode. Or we can also define like this. It is the reciprocal of slope of IV characteristics of a diode. IV characteristics of a diode. Right? See the IV characteristics of a diode in forward bias actually. This already we discussed, right? What is the slope for this curve actually? The slope is nothing but di by dv. Right? See here, just consider a small portion here. I think this is nothing but di and this is nothing but dv. Right? Now what is the slope here? Slope is nothing but di by dv. Right? Simply in mathematics, slope is nothing but dy by dx. Right? Like that here, di by dv. Okay. Now how to calculate this slope here? Okay, for calculation of this slope here, consider a diode current equation. Consider a diode current equation. We know what is the diode current equation? I equal to I naught into e power v by eta into vt minus 1. Okay. Now see here what you will do. Differentiate above equation with respect to what? With respect to v. Then di by dv equal to I naught into what is the differentiation here? 1 by eta into vt e power v by eta into vt. What is the differentiation of 1? 0. Okay. See here from this expression, what is this value? I naught into e power v by eta into vt. This value is nothing but from this expression, from the diode current equation. This is simply I plus I naught. Now what it is? di by dv equal to I plus I naught by eta into vt. Right? So here this is the slope, right? Substitute this slope. Then what is RAC here? RAC is nothing but what? 1 by I plus I naught by eta into Vt. Then what is RAC here? Eta into Vt by I plus I naught. Yeah, this is equation of what? Dynamic resistance. You know, this dynamic resistance is calculated under presence of AC source, right? That's why it is also called as small signal resistance. Small signal resistance and dynamic resistance both are same. Okay. And one more actually, what is the dynamic resistance in case of forward bias? One more point actually. What is the dynamic resistance in case of forward bias? See, when the diode is in forward bias, when diode is in forward bias, what is the dynamic resistance here? The dynamic resistance RAC is equal to, okay, eta into Vt by I. Because in case of forward bias, the reverse saturation current almost negligible, right? Because the current is due to only majority charge carriers, right? That's why the dynamic resistance is nothing but eta into Vt by I. But you know, the very interesting here, this I is nothing but a DC parameter. This is, we are calculating in the presence of AC, right? This is a DC parameter. Eta into Vt by I, where Vt, I think you know, thermal voltage. The thermal voltage is nothing but 26 millivolts at room temperature. Or we may consider like this, the expression of Vt is nothing but Kt by Q. Okay, yeah, copy. Right down here, dynamic resistance. It is the ratio of change in voltage across the diode to the change in voltage across the diode to the change in current through the diode. Change in current through the diode. That is RAC is equal to dV by di. RAC equal to dV by di. Or it is the reciprocal of slope of IV characteristics of a diode. 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 Right. Yeah. Copy here. That is RAC is equal to 1 by di by dV. RAC equal to 1 by di by dV. Right. Yeah. Next, copy this one. Copy this one. Right. Next, a copy up to here. After that, finally here. Yeah, copied, copied, right? Yeah, write down a question here. One an example. Write down. A germanium diode has a reverse saturation current of 25 nanoampere at a room temperature. And it is operating at forward bias of 0.7. And it is operating at forward bias of 0.7. Calculate static and dynamic resistance. Calculate static and dynamic resistance. Right. Yeah, all of you read the question. Copied, right? Yeah. See, what is given data first? What is our given data actually? I think they given germanium diode having a reverse saturation current of how much? 25 nanoampere. This is at room temperature, right? At room temperature, I think you know VT equal to 26 millivolts. And next, also they given operating voltage, that is V, right? How much? 0.7. Okay, they given 0.7. Now, what you want to calculate here? Static and dynamic resistance. So here, before calculating static resistance, first calculate current through the diode, right? We know V, but we don't know I. Huh? Then what is current through the diode actually? I equal to I naught into e power V by eta into Vt minus 1. I naught is nothing but how much? 25 nano ampere. E power V is 0.7. Germanium na, so eta is 1. And Vt 26 millivolts minus 1, which is approximately equal to how much here? 12.3 milliampere, right? 12.3 milliampere. Next, what is static resistance? Static resistance is nothing but RDC, which is equal to V by I. What is V here? So V is nothing but 0.7, I is nothing but 12.3 milliampere, right? So which is equal to how much? This is 56.86 ohms. This is our static resistance value. Huh? Similarly, what is dynamic resistance actually? So dynamic resistance is nothing but RAC is equal to eta into Vt by I. Yeah, actually you have a doubt. See, how you know whether the given diode is in forward bias or reverse bias actually depends on V and I value. See here, I think we got V, I is positive, right? Also they given V equal to also positive. When V is positive, voltage across the diode is positive and current through the diode also positive, means the diode is in which bias? Forward bias. Okay. So in this way we can identify whether diode is in forward bias or reverse bias while solving questions, right? For germanium eta is how much? 1. Vt is 26 and I is nothing but 12.3, right? Milliampere. So what is the answer? 2.11 ohms. This is the dynamic resistance value. Sometimes they're asking like small signal resistance. Both are same. I already told now. Small signal resistance and dynamic resistance both are same. Yeah. Yeah. Copy. Yeah. So with this problem, diode resistance is completed. And next topic, diode capacitance. Next topic, diode capacitance. Yeah, before going to diode capacitance, means how diode acts as a capacitor. So first we know about what is a capacitor, right? So what is the use of the capacitor? See, the purpose of the capacitor is to store the charge, right? What is the purpose of the capacitor actually? To store the charge. I think the storing charge is varied with respect to what actually? With respect to your applied voltage. With respect to your applied voltage, means if your applied voltage is varies, the storing charge also varies. Then what is capacitance actually? Capacitance is nothing but the rate of change of charge with respect to applied voltage is called as what? Capacitance. What is capacitance? The rate of change of charge with respect to applied voltage is called as capacitance, right? First write on this point. Capacitor is used to store the charge. To store the charge. The storing charge is the storing charge can be varied. The storing charge can be varied with respect to applied voltage. The storing charge can be varied with respect to applied voltage. Next, the rate of change of charge with respect to applied voltage. The rate of change of charge with respect to applied voltage is called as the rate of change of charge with respect to applied voltage is called as capacitance. Is called as capacitance. That is C equal to dq by dV. C equal to dq by dV. Right? Yeah. Now coming to diode capacitance. You know, diode exhibit two types of capacitance. One is transition capacitance, another one is diffusion capacitance. Right? Here, when the diode exhibit transition capacitance, when the diode exhibit diffusion capacitance. See, in case of forward bias, it exhibit diffusion capacitance. In case of reverse bias, it exhibit transition capacitance. Yeah. In forward bias, how diode acts as a capacitor. In reverse bias, how diode acts as a capacitor. In detail, we will see, right? Yeah. Write down first. Diode exhibit two types of capacitance. Two types of capacitance. The first one, transition capacitance. First one, transition capacitance, and second one, diffusion capacitance. Diffusion capacitance. Yeah, put the heading transition capacitance. Transition capacitance. This is also called as junction capacitance. This is also called as junction capacitance. That's why it is denoted with CT or CJ. Sometimes in problems they are represented as CJ. It is also correct. That is also a transition capacitance. Right. Transition capacitance. Yeah, Suro here. See, when the diode exhibit transition capacitance, I already told you, when the diode is operated in reverse bias, right? Yeah. In reverse bias, how diode acts as a capacitor? In reverse bias, how diode acts as a capacitor? See, please recall reverse bias operation of PN diode actually. See here, when reverse voltage is increased, what happened? Depletion region is increased. Am I correct or not? Depletion region is increases. Yeah, what depletion region contain? Immobile charge. What depletion region contain? Immobile charge. That means this immobile charge is varied. This immobile charge is varied with respect to what? Applied voltage. See, if you are varying your reverse voltage, your depletion region increases, right? That means immobile charge is varied, right? So that means here this immobile charge is varied with respect to applied voltage. Here the charge is varied with respect to applied voltage is nothing but what? Capacitance. Yeah, this capacitance is called as which capacitance? Transition capacitance. This is also called as what? Junction capacitance, because here immobile charge is varied at the junction. That's why it is also called as a junction capacitance. Right? So this is equal to what? CT or CJ is equal to dq by dV, where dq is nothing but change in immobile charge, okay, and dV is nothing but change in the applied reverse voltage. Yeah, right now. When the diode is in reverse bias, it exhibit transition capacitance. It exhibit transition capacitance or junction capacitance. Junction capacitance. Yeah. Next point. When the reverse voltage is increased, when the reverse voltage is increased, then depletion region is increases. That is, immobile charge within a depletion is increased. Immobile charge within a depletion region is increased. Next point, This immobile charge is varied. This immobile charge is varied with respect to applied reverse voltage. Therefore, this rate of change of immobile charge, with respect to applied reverse voltage is called as transition capacitance. Right? That is CT or CJ is equal to dq by dV. Where dq is the change in immobile charge and dV is the change in applied reverse voltage. Yeah. How to compute this transition capacitance value? How to compute? Here, to compute this transition capacitance, right? Consider depletion width, equation of depletion width. So here, what is the depletion width in case of PN junction? Already we derived this depletion width also, right, in my previous lecture. What is W here? W is nothing but 2 V0 epsilon by Q into 1 by Na plus 1 by Nd. 1 by Na plus 1 plus Nd, right? Here, just now I told actually transition capacitance is exhibit in which bias actually? Reverse bias, right? See here, in case of reverse bias, you know this V0 become VB. This V0 is nothing but VB, you know, where VB is nothing but what? V0 plus V. Also, to calculate transition capacitance, here consider one-sided heavily doped PN junction. One-sided heavily doped PN junction means either it is P plus N or PN plus. Either it is P plus N or PN plus. Here I am considering P plus N. P plus N means P side is heavily doped compared to N side. Actually. Now, see from this data actually, from our assumptions, what is our depletion width actually? Depletion width is nothing but 2 into, this is simply V0 plus V by Q epsilon into 1 by Nd, because this Na is almost very far, means a high value compared to Nd, then 1 by Na is almost 0, so it is approximately 1 by Nd. Okay, so from this, what is V0 plus V here? V0 plus V is nothing but simply it is W square Q into Nd by 2 epsilon, right? Now what we will do here, differentiate above equation with respect to W. So differentiation of this value is constant, right? See, differentiation of constant is nothing but 0, because V0 is fixed, right? 0.7 or 0.3, it is fixed, so it is 0. Now I think which is varying here? If reverse voltage is varying, right? So this is simply dV by dW, which is equal to 2 into W into Q into Nd by 2 epsilon. Here 2 cancel. Then finally, what is dV by W here? dV by W equal to WQ into Nd by epsilon. Yeah, consider this one as some equation 1 here. Some equation 3. Consider this one is equation 1 and consider this one is equation 2. Right? Yeah, next one. See, in case of depletion region, actually, which charge carriers are present? Actually, immobile charge, right? Yeah. What is the amount of immobile charge present in a depletion region? The amount of immobile charge present in a depletion region is given by, how to calculate here? This is simply, we know, see all of you. What is rho v here? Rho v is nothing but n into E, for example. Charge density is nothing but Q into rho v equal to n into E. What is rho v here? Charge per unit volume, right? But actually here we want charge per unit area, right? That is Q equal to, this can be written as, so V into Ne, right? So immobile charge in a depletion region is given by, so N into E into volume, right? What is this N here? This N is nothing but Nd. E is nothing but charge of electron, or we can also say, we can also represent it as Q here. Here we can consider as Q charge of electron. Okay. And volume, what is volume here? Volume is nothing but W into N into W into A. Simply it is W into A. Width into area, nothing but volume actually. This is the immobile charge, amount of immobile charge present in a depletion region. Okay. Now what you will do here, differentiate the above equation with respect to what? W. dq by dw is nothing but what? Nd into q into Na. Right? Yeah, consider this one as equation 4. Okay. Now what is transition capacitance actually? dq by dv. Right? dq by dv. So I think it can be written as, dq by w into dw by dv. What is dq by dv here? Nd into q into A. What is dw by d? Right? So this is epsilon by w into q into nd. So here q into nd cancel. Now what is the final expression here? Here the final expression is nothing but Ct equal to epsilon into A by w. Yeah, this is what actually transition capacitance value in case of reverse bias condition. See, this much of capacitance is present. See, substitute W value, that time actually whatever the voltage you are applying, and area and epsilon and permittivity, then you will get the transition capacitance. Right? This is also called the junction capacitance. So in this way we can compute the transition capacitance value. Right? Yeah, first write down. I will tell you one by one. Yeah. Write down. Write down this. To compute transition capacitance, consider one-sided heavily doped p-n junction. Consider one-sided heavily doped p-n junction, that is in bracket p plus n in reverse bias condition. Next point, the depletion width of the p-n junction is given by equation is given by copy this equation here, directly copy this equation. Directly copy this equation. Yeah, after that copy this equation, copy up to here, up to equation 2, here, up to equation 2. Yeah, next one, write down the amount of immobile charge present in a depletion region can be written as the amount of immobile charge present in a depletion region is given by is given by, yeah, copy this value here. Q immobile is equal to N into Q into volume. I think who I hope that everybody is understand, right, how we got this expression from this. We know rho v equal to N into Q, but we know rho v is nothing but Q by V. From this, Q equal to N into E into V, right? Yeah, copy here. If you want, you can also copy this one also.